In this video, we are going to talk about lopital rule. What is lopital rule? Lopital rule is the rule that help quickly and effectively solve the situations of limits when it facing uncertainty of type 0 over 0, infinity over infinity, or negative infinity over positive infinity, or positive infinity over negative infinity, or negative infinity over negative infinity. Okay. So in the idea in a powerful method, lopital powerful method, is to when you face the limit of type these following types of uncertainty, you can take the derivative of that function, and that should eliminate this uncertainty. But sometimes can be cases when it doesn't eliminate uncertainty. Then you can take one more time derivative. They say it's better see one time than here 10 times. So let's start working, and I will show on examples. First one, we have limit x approaches to 0, e to power 2x minus 1 over x. Look, if I plug the x is 0, e to power 0 minus 1, right? E to power 0, it's going to be 1. 1 minus 1 divided by 0. We are getting 0 over 0, yes? Let me point in a different color so we would see. Oh, no, doesn't look good. Okay, so therefore in this case we can apply L'Hopital rule. So which means limit x approaches to 0, and we are taking now, what is interesting here in L'Hopital rule, we have to take, let's say, let me write down the limit itself. So once we have limit x approaches to c, f of x over, let's say, g of x. So L'Hopital rule allows to take limit x approaches to c, but we take derivative f prime of x over g prime of x. Now, what is important here to mention that sometimes people occasionally use L'Hopital's rule incorrectly by applying quotient rule. So using quotient rule like f of x over gx prime, which would be equal f prime g minus g prime of f divided by g squared. You cannot apply, this is not the L'Hopital rule. L'Hopital rule is separating, as you can see, separating numerator, separating denominator, and taking separate derivative of numerator and derivative of denominator. So please remember that. It's a very common mistake sometimes, or when students it's solving, it's or facing dilemma, should it apply separate or it should apply as the apply quotient rule. Okay, so now once I said that, back to our problem. It's gonna be equal, I'm going to write down step by step so you would see, d by dx for e to power 2x minus 1, And denominator would be d by dx. As you can see, two separate derivatives of x. So what do we get? We get limit x approaches to 0, derivative of e to power x is equal e to power x. So, which means when I apply, I'm going to get, it's going to be e to power 2x, and since it's a chain rule, then I have to take derivative of 2x, right? Which is going to give me 2, and these 2 I put in front. And derivative of 1 is 0. And in denominator, derivative of x is 1. And the answer is going to be 2e to power 2x. Okay? Let's solve another derivative. Another example with limit, where we will have the case of 0 over 0. So, we have limit x approaches to pi over 4, tangent x minus 1 over sine 4x. So if we plug, so tangent pi over 4, let me see, limit x approaches to pi over 4. Here we get tangent of pi over 4 is 1. You don't have to memorize it. All you have to know that when it's come to pi over 4, which is 45 degrees, sine pi over 4, tangent is a sine over cosine, right? And in the case of pi over 4, it's a 45 degrees. It's half and half, right? So it's cosine and sine are equal, square root 2 over square root 2. And that's where from tangent 45 is coming 1, okay? Therefore, it's going to be equal 1 minus 1, and sine 4 times pi over 4. So 4 and 4 is gone, and sine pi is how much? 0. We get 0 over 0 combination. Therefore, we can apply L'Hopital rules, right? We always have to check if L'Hopital is applicable or not, because L'Hopital is applicable only on these uncertainties, 0 over 0 and all combination of the infinity over infinity. So either very small cases or very large cases, 0 over 0 and infinity over infinity. Okay, so let's apply. So we proved that we can apply, we showed that we can apply L'Hopital rule. This is going to be equal limit x approaches to pi over 4, tangent x minus 1, sine 4x. So we are going to apply L'Hopital. Yes, and it's going to be limit x approaches to pi over 4. We are taking derivative d to power dx for tangent x minus 1, and d by dx for 4x. Okay, sine 4x. All right, so this is going to be equal limit x approaches to pi over 4, and derivative of tangent x is a secant x, secant square x, right? Let me add here, tangent x prime is a secant square x. So secant square x, derivative of 1 is 0, and we divide by derivative of sine 4x. So derivative of sine is cosine x, right? So it's going to be cosine 4x, and then since it's a chain rule, instead of x we have 4x. That's mean we have get inside and take derivative of 4x, which is going to be 4 cosine 4x. Okay, now let's plug. Let's see if uncertainty 0 over 0 eliminated. We are getting secant squared pi over 4 times cosecant 4 times pi over 4. So right away I'm going to cancel this 4 over 4, and what we are getting here, secant squared pi over 4 is 1 over, since let's assume I don't remember how much it is, and nobody is obligated to know, but as long as you know sine, cosine, everything else, tangent, cotangent, the secant, cosecant can be calculated. So it's exactly what I'm doing. I'm dividing 1 over cosine squared pi over 4, right? Because secant is a 1 over cosine pi over 4, and here will be 4 cosine pi. Okay, cosine squared pi over 4 is equal, let's see, let's calculate. Cosine squared pi over 4 is square root 2 over 2, right? Because 45 degrees squared. That is going to be 2 over 4, which is going to be 1/2. Yes? Okay, this is equal 1/2 on the top. At the bottom we have 4 times cosine pi. Cosine pi here, it's going to be -1, right? Times -1. And we are getting 1/2 times 4. Oh, 1 divided by 1/2. I'm sorry. Let me fix here. 1 divided by 1/2. See, this is this 1. Okay. Let me bring down. Okay. I'm going to clean this anyway. It's a drafting. And we already know cosine pi is -1. So this is going to get 1 stays on the top, 1/2 comes to the bottom, because what we are doing, 1 over 1/2 is equal what? 1 divided by 1/2, it's going to be 2, right? It's going to be 2. Okay. I'm trying to jump, but then I'm coming back and changing my mind. 2 over 1 is equal to. So it's going to be 2. So not to jump, let me write down here, this is going to be 2. And at the bottom I have 4 times -1. Okay, I made it. I didn't miss any step, so it can be clear. Let me now clean this drafting. And I have here 1, this is 2, and the result is -1/2. And here we have -1/2. Okay. Next, limit x approaches to e. We have 1 minus cosine pi x over e to power natural log x minus 1 over x minus e. Okay, here, see, I have practically 2 problems to solve. This is one, and this is another one, because it's a whole expression there. So let's do it. Limit x approaches to e, 1 minus cosine pi x over e is equal. So if I plug e now, 1 minus cosine pi e over e, yeah, this e is gone with this e, and we are getting cosine pi is -1, so minus -1, and we get 2. Okay, here we are good. Now let's solve the exponent. Exponent is a different story. That's why I chose that one. It's interesting. So limit x approaches to e, natural log x minus 1 over x minus e. So let's plug e here. We are going to get log e minus 1, e minus e. So natural log of e is equal 1, right? Because the base is e, so you have to take e to power 1 to get e. Therefore, we are getting 1 minus 1 over e minus e is 0, 0 over 0. This is where we have 0 over 0. Therefore, we can apply L'Hopital rule. So that is equal limit x approaches to e. Here we have d by dx, natural logarithm x minus 1. Here we have d by dx, x minus e. Okay, so let's see what result we get. The derivative of natural log x is 1 over x, right? Which means from here we are getting limit x approaches to e. 1 over x, derivative of 1 is 0 because it's a constant. Now derivative of x in denominator is equal 1. And derivative e by base x, then e is acting as a constant, right? Let me do here, the e by x. E has nothing to do with x, so it's a constant. If it would be free, it would be same way, so it's going to be 0. So, we are getting result 1 over x divided by 1, result is going to be 1 over x. And if we plug now the limit x approaches to e, we will get 1 over e. Okay, all right, so now we can put together. So in a we solved the derivative, we solved the limit of base 1 minus, let me clean this, and I'll use in a we solved the limit of base, and we got here 2. And in b we took a limit of exponent, and we got 1 over a. So the final answer, limit of x approaches to e, 1 minus cosine pi x over e to power natural log x minus 1 over x minus e is equal to power 1 over e. And that's it. We arrived. Next, we are going to take limit for the expression that gives gives us infinity over infinity, which means enormously large numbers, right? So we have, let me see, it's free. Let me change the color of this notation so you can easily find it if you want to rewind forth forth and back. So problem number 4, we have limit x approaches to infinity, and we have natural log x over x. That is giving us infinity over infinity, yes? Okay, so this is going to be equal limit x approaches to infinity, and we get natural log x prime over x prime, right? Result is limit x approaches to infinity. Prime, the derivative of natural log x is 1 over x, and derivative of x is 1. So if we plug infinity, we are going to get 1 over infinity, and here is 1. So 1 divided by infinity, we get 0. And that is going to be our answer. Now, example 2. Okay. So what do we have here? Limit x approaches to infinity, yes, e to power x over x squared. Yet again, we are getting infinity over infinity here, right? And we are solving e to power x prime over x squared prime derivative. So that is equal. Okay, I forgot to put limits. Do you think only you are doing silly mistakes? Come to me. I do them all the time. Math and silly mistakes are going hand by hand. Okay. There we go. So this is equal. We are taking derivative, and what we get? Limit x approaches to infinity. Derivative e to power x is e to power x, and derivative of 2x is 2, and the result is e to power infinity over 2, and this is equal infinity. Now I would like to look at the cases of one-side limits. What if I have limit x approaches to infinity, positive infinity actually, and I have e to power positive infinity would be here over 2, we get positive infinity result. And if I have limit x approaches to negative infinity, I will have e to power negative infinity over 2, which would be 1. Since I'm dealing with infinity, I'm ignoring this to 1 over e to power positive infinity, which is going to be 0. Number 6, and we have limit x approaches to positive half a pi, and we have tangent 3x over tangent x. Okay, so if we plug half a pi, tangent half a pi, 3 times even half a pi, doesn't matter, you still will end up with half a pi, and dividing by tangent the half a pi, positive 1. So we end up with infinity over infinity, right? Okay. Let's see how we're gonna work with it. So we are taking limit x approaches to pi over 2. Since it's a pi over 2, so then we take it as a positive one. So it's going to be derivative of tangent 3x over tangent x derivative. So it's going to be equal limit x approaches to half a pi. So, and that is going to be 3 over cosine squared 3x, right? And here we get 1 over cosine squared x. How did we get that? We know that derivative of tangent x is secant squared x, right? Okay, and secant is 1 over cosine, correct? So tangent 3x, let's do drafting. Tangent 3x, it's going to be secant square x, right, times derivative of 3x. So is equal, secant square is 1 over cosine, well, since it's 3x, let me put 3x, cosine squared 3x, right, and times derivative of 3x is 3. So this is equal 3 limit x approaches to half a pi cosine square x over cosine squared 3x. Well, and we are getting 0 over 0 yet again. So what in this case? Why 0 over 0? Because cosine half a pi is 0, right? And cosine squared 3 times half a pi, it's same 0. Because it's going to be how much? 3 over 2, 270 degrees, right? Okay, cosine is 0. Okay, so which means I'm going to simplify, again, take another derivative, apply another L'Hopital rule. It's going to be 3 limit, oops, this is supposed to be, we are getting x approaches to half a pi. Okay, and derivative of cosine square x over cosine square 3x, that is equal 3 limit x approaches to half a pi, and we get 2 cosine cosine x. Let me these two make looks, it's like really squared, otherwise I was getting confused myself taking as a cosine 2x. So 2 cosine x times and derivative of cosine x is going to be negative sine x, right? First I took derivative of this square, and second I took derivative of cosine itself. Here in denominator I will get 2 cosine 3x, right? And then I'm taking 2 cosine 3x, and then I'm taking derivative of cosine 3x, which means derivative of cosine 3x is negative sine 3x, and derivative of 3x is going to be 3. We got it? Let me write down here in details just in case to do drafting. Let me clean this drafting here, and I'm going to do drafting here. So cosine square 3x is equal 2 cosine 3x times derivative of cosine 3x times derivative of 3x. And we are getting 2 cosine 3x, because look, we take derivative, first we are taking derivative of these 2, and then take derivative of cosine 3x, and then take derivative of 3x. Okay? So cosine 3x times derivative of cosine 3x is negative sine 3x, and derivative of 3x is 3. So we are getting equal limit. This 3 and negative 3 will be cancelled, right? Because this 3 has nothing to do with limit. So we are going to get limit x approaches to half a pi. So negative with negative, it's going to cancel, right? And we are getting cosine x. Oh, these two also will be cancelled. So we have cosine x times sine x. In the denominator, we have cosine 3x times sine 3x. Yes? Okay. So if I plug, okay, well, I can plug everything might as well. So it's equal cosine half a pi, sine half a pi, cosine 3 pi over 2, and sine 3 pi over 2. Now, what do we get here? It's going to be 1. It's going to be negative 1, because this one is at the pi over 2, right? Right here, sine is 1. This one is right here, 270 degrees, sine is negative 1. Okay? Now, regarding cosine here, cosine here is 0, right? Cosine 90 degrees is 0. We are getting 0. Cosine here also 0. We are getting another 0 over 0. Beautiful. Third time we have to go over. Okay, so we are going over one more time. Hopefully this will be last time. Equal negative limit. I'm taking x approaches to half a pi. This is going to be cosine x prime over cosine 3x prime equal negative limit x approaches to half a pi. Derivative of cosine is okay. Wait, this negative. Yeah, this negative I forgot to apply here. So we have here negative, right? So this negative gonna stay. Oh, I have it here. Okay, this negative I applied. Very good. I put this negative. This is this negative here. Very good. Negative limit x approaches to half a pi. Derivative cosine negative sine x. Negative 3 sine 3x. So sine x is approaching to 1 if I plug half a pi. Sine 3x approaches to negative 1, right? Because 270 degrees. And we have practically negative. Here we have 1 over negative 1. And the answer is going to 3. And the answer is going to be 1 over 3. Well, I also did quite a few silly mistakes because I had enough, to be honest with you. Anyway, so I'm done. We don't have any other mistakes here. Let me double check to make sure of these negatives. So these negatives come here. Let me make clear. This negative, it's in numerator, because here this negative with this negative is going to be free, although it doesn't matter for the fraction per se, but so you would see where from this negative moved. Otherwise doesn't matter. You can put negative in numerator, denominator, meaning doesn't change. But I'm thinking you would, if once you see in denominator, you will start looking where from in denominator popped up. No, that's a numerator. Okay, negative 1 over 3, and the answer is positive 1/3. Okay, so what is interesting here, that initial uncertainty, infinity over infinity, that we started at the beginning, where is it here? After first differentiation, turn into uncertainty 0 over 0, look here. And the lopital rule, it's applied further yet again. Yes? And then we applied another 0 over 0, so we practically took how many times? 1, 2, and then 3 times we had to apply to receive the answer. Okay, so we are good. Thank you very much for watching. I am done, and I really appreciate your patience. My patience was running out already. So anyway, thank you for watching, and I'll see you in next video.